Good morning. In this video I'm going to try to use Mathematica to create a dot going around in a circle. I have to review the graphics primitives a little bit because it's been a while since I programmed in a Mathematica. Okay, while we were paused, I got a rudimentary graphic plot. I've got a circle at coordinates 1, 1 with a radius of 0.1. I made the plot range go from -2 to 2 and -2 to 2 in the vertical. I turned on the axes so you could see where that was. Okay, and the only other thing I'm going to do is change, instead of putting it at 1, 1, I'm going to put it at sine theta, cosine theta, cosine theta, sine theta. Then I'm going to add a manipulate command that makes it so I can adjust the value of theta from 0 to 2 pi. And now you can see that as I change this theta value, it makes that circle go around in a circle. Alright, now I'm trying it out with the animate command. And this time I've added a 0.1 so it knows exactly how much to add for each animation frame. But what I'd actually rather change than the theta directly, what will constantly go forward all the time, is time. So I'm going to have this thing go forward from 0 to, say, 1. And I guess we'll still have it to go forward in frames of 0.1. I don't know exactly how long the frame is, but we'll just pretend that each frame is 1/10 of a second. And what I'm going to put in here instead of theta is omega. Omega times t. And then before it starts animating, I'm going to say that, say, omega is 1. And what this is going to do is it's going to go 1 radian per second, or 1 radian every 10 frames is what that's going to amount to. So now you can see it going at 1 radian every 10 frames. And I guess it's starting over because it's only going up here to 1 radian and coming back and starting over from the beginning. Alright, so let's make it so that omega is 2 pi. Then it will go all the way around the circle in 10 frames. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4. Of course, if I set it to be 4 pi, it'll go around the circle twice in 10 frames. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 5, 6, 7, 8, 9, 10. So anyway, this is actually technically 4 pi radians per second, or per 10 frames. So this is an angular velocity. So here's something else I'd like to show you. We have this displacement vector, r, that is varying in time by going around in the circle. It's cosine omega t, sine omega t. Okay, what I'm going to do now is to take the derivative of that vector with respect to time. The change in position of a particle with respect to time is called its velocity. So I'll call it v of omega comma t colon equals underscore underscore, and we want to make sure it shows it, and shouldn't show any change on the screen. And then after that we want to see the acceleration vector. So let's go ahead and plug this in down. Whoops. Down here we'll have a of omega t equals the derivative of v of omega t, and then show it. And we find out that this acceleration vector is the same as the position vector. It has cosine t omega and then sine t omega. Let's find out what we get if we take these and divide them. I don't think this is going to work, but a of omega t oops, divided by x, or no, r of omega comma t. And okay, it did work. It's showing us negative omega squared, negative omega squared. That is to say the acceleration vector is equal to omega squared. Sorry, that is to say that the acceleration vector is equal to omega squared times the opposite of the position vector. So that means the acceleration necessary to get a body to go in a circle is omega squared times r, where r is the radius of the circle you want it to go in, and omega is the radial velocity that you want it to go at. So that acceleration requires a force, and that force might be achieved by applying tension, or gravity, or friction, or a normal force, or an electric or magnetic force. Well, I've carried on for long enough this morning. Hope you enjoyed.